IR spectroscopy. This IR spectroscopy, also called as vibrational spectroscopy, and the total IR region is around 14,000 centimeter inverse to 33 centimeter inverse, and this total IR frequency region is divided into three types. One is near IR. The range of near IR is 14,000 centimeter inverse to 4,000 centimeter inverse, and the second one is middle IR. Middle IR frequency range is 4,000 centimeter inverse to 600 centimeter inverse, and the third one far IR. The far IR range is the 600 centimeter inverse to the 33 centimeter inverse. Okay, of this total IR region, the middle IR region is sufficient for the IR spectroscopy, and when sample is a sample molecule, when interact with the middle IR, when sample irradiated with the middle IR produces this IR spectrum, means the sample is irradiated with the middle IR range of radiation or frequency and once we are irradiating this sample with the middle IR, in this molecule the vibrational energy levels will be changes. Vibrational energy levels are changing. This middle IR energy is sufficient for the changes in the vibrational energy levels. That's why we are calling this IR spectroscopy also vibrational spectroscopy. Means this middle IR energy is sufficient for the changes in the vibrational energy levels. Okay, that's why we are calling this one as a vibrational spectroscopy also. Okay, and which of the molecules are IR active and which of the molecules are IR inactive? See, molecules with permanent dipole moment value, dipole moment is mu is not equal to 0. The permanent dipole moment, it causes having the permanent dipole moment or induced dipole moment. Molecules with a permanent dipole moment and molecules with induced dipole moment are IR active molecules. Means they shows the IR spectrum. IR active compounds. Molecules with permanent dipole moment or molecule with induced dipole moment are IR active. Means examples. For example, HCl molecule is there. HCl molecule. In the HCl, we have this partial positive and the partial negative charge because these having the permanent dipole moment value. Okay, or HBr also like this. These are the molecules with the permanent dipole moment. That's why they are IR active. And second one, we are taking the carbon dioxide. Is a what? C double bond O, C double bond O. This is a CO2 molecule, and this molecule generally doesn't have the dipole moment. Okay, zero dipole moment. But when the vibrations are taking place in the molecule, if the vibrations are taking place, is there any changes will be taking vibrations in the molecule? At that time, by the induced dipole moment, it will produce is not zero when vibrations are taking place. Means this carbon dioxide molecule shows induced dipole moment by the vibrations in that molecule. Due to vibrations, it is shows induced dipole moment value. That's why this is also generally it having zero dipole moment. Basically, it is a IR inactive, but at the time of vibrations in the molecule, it is IR active molecule. Means due to vibrations in the molecules produces induced dipole moment value. Okay, the next molecules with zero dipole moment. Zero dipole moment means mu is equal to 0. Okay, molecules with zero dipole moment are IR inactive. IR inactive. Examples: H2 molecule or N2 molecule. Means H2 means there is no partial positive and there is a what? No polarization. This is N2 nitrogen. N triple bond N. This is a nitrogen molecule. Means in this molecule mu is equal to 0 na? Because there is no polarization. Okay na? This is a, but in this the polarization is possible. This is a more electronegative atom. This is a less one. That's why this is a polarization is possible. That's why they have the dipole moment value. Somewhat dipole moment value is there. But these molecules have with a zero dipole moment. That's why they are IR inactive molecules. Means we are saying IR active and inactive based on the dipole moment of the molecule. If molecules with permanent dipole moment as well as by induced dipole moment also it have, they are IR active. If molecules with zero dipole moment, no dipole moment, they are IR inactive molecules. And see, and this is a IR spectrum. This IR spectrum is what? Is a two-dimensional spectrum, and in this on y-axis we are taking the percentage of transmission, and this is a wave number. We get the dips in the spectrum. Okay, these dips in the spectrum are called IR bands. Or IR peaks. Okay, these dips in the spectrum is or IR bands or IR peaks. Where the spectrum is taken between the percentage of transmittance and the wave number, we get the some dips in the spectrum. The dips in the spectrum is called IR bands or IR peaks. And the major application of this IR spectrum is for the functional group detection. Functional group detection means IR spectrum is mainly used for the functional group detection. Means which type of functional groups are present in the molecules we can find by using the IR spectrum. Means different functional groups have a different vibrational frequency level. By the use of these frequency values, we can find which type of functional group present in the molecule. Means this IR spectrum, there is a vibrational spectroscopy, is mainly used for the identification of functional group, which type of functional groups are present in the molecule. Okay, and in this the total middle IR range is what? Around 600 to 4000 centimeter inverse. That is the middle IR that is sufficient for the changes in the vibration energy levels. And of this total, this is about 600 centimeter inverse to, this is a what, 4000 centimeter inverse. In between 4000 centimeter inverse to 1500 centimeter inverse, that is called functional group region, functional group region. And this 1500 centimeter inverse to is a 600 centimeter, is called fingerprint region. Okay, this the next what are the types of vibrations that takes place in the molecule? Types of vibrations. Okay, there are two types of vibrations in IR spectroscopy. Okay, in IR spectroscopy, two types of vibrations are possible. One is stretching vibrations, and second one is bending vibrations. Okay, and these stretching vibrations are again classified into two types. One is symmetrical stretching, then asymmetrical stretching. Okay, symmetrical stretching and asymmetrical. Then bending vibrations are again classified into four types. One is scissoring, next rocking, next wagging, twisting. Out of these four bending vibrations, scissoring and rocking are in plane bending vibrations, and wagging and twisting are out of plane bending vibrations. Total vibrations in this IR spectroscopy are classified into two types. One is stretching vibrations and bending vibration. The stretching vibrations are again classified into two types. One is a symmetrical stretching and asymmetrical stretching. Then bending vibrations are classified into four types. One is the scissoring, rocking, wagging, twisting. Out of these two, scissoring, rocking are in-plane bending vibrations, and wagging and twisting are out-of-plane bending vibrations. Okay, we will discuss each and one. What about the symmetrical stretching? Stretching vibrations. Vibrations causes, due to vibrations, there is change in the bond length. Due to stretching, the bond length will be changes. Okay, the type of changes are called stretching vibrations. Due to vibrations in the molecules, if bond length is changes, the type of vibrations are called stretching vibrations. Okay, for example, out of this, what is that? First one is about symmetrical stretching. What is the symmetrical stretching means? Symmetrical stretching. What is symmetrical stretching means? For example, a molecule we are taking. Okay, is a molecule A with these central molecules. With this, the two atoms are attached to this one. For example, the symmetrical stretching means same two atoms are, if we are pulling to outside, otherwise the same way the atom is pulling to outside, this in symmetrical stretching the two atoms are moves on the same direction, either in outside or inside. With this, what happens, the bond length will be changes. The changes in the bond length occurs, the same directional changes in the atoms, it may be inside or outside. This is what symmetrical stretching. Okay, then go to the asymmetrical stretching. Asymmetrical stretching. In asymmetrical stretching, the two atoms are moves in opposite directions. One is outside, one will be inside. Otherwise, it will be inside, it will be outside. Okay, the two atoms are moves in opposite, in different ways, inside and outside. This is asymmetrical stretching. With this, the bond lengths are changing completely. The stretching vibrations means the bond lengths will be changes. The symmetrical stretching means either the two atoms are stretched in same direction and will be different directions. Okay, one is inside and the another way outside. This is asymmetrical. Symmetrical means both the atoms are maybe outside or inside. Symmetrical stretching. Come to the bending vibrations. Bending vibrations. Okay, vibrations causes change in bond angle. Change in bond angle are called bending vibrations. Due to vibrations, if the bond angle changes, the type of vibrations are called bending vibrations. Okay, and what are the types of bending vibrations? Scissoring, rocking, wagging and twisting. Okay, come to the scissoring. Okay, and these are what in plane bending vibrations. Scissoring. What is scissoring means here? With respect to this is a molecule, this is a what? Two atoms are attached to this one. Scissoring, we know that what is the as the same way of scissor. How the scissor will becomes here? The two will be in this way. Scissoring. Okay, like this. If it is comes inside, it will become this side. In plane, within the same plane. See, this is the way. Scissoring. Like this. In plane, same directional, in same opposite directional rotations. Opposite directions is what? Scissoring. As this, bond lengths will be changing or not? Bond angles will be changes. Like this. This was inside, this is also inside. This is say in plane, opposite directional is scissoring. Okay. Next, what is rocking? With respect to this molecule, in this molecule is one is a what? and this is the same direction, like this. If it is a molecule is there, it will be same type of rotation, like here only both will be this side, otherwise both will be this side, or same directionals in plane, same directionals rotations is rocking. Here also the bond angle will be changing. What is that? Scissoring means in plane opposite directionals is scissoring, is a in plane up same directional rotations is rocking. Next come to the wagging. What is wagging means here? I am writing this wagging. See, what is that means? These are what? Out of plane bending vibrations. Out of plane means here what? With respect to this one, see, this is one will be there, come up above. So what? If two atoms are come above, okay, I am writing with the same positive signs. Out of plane, in previous what, they are in the same plane only, they are moving, either scissor model or the same type of, okay. But here what? Wagging means out of plane vibrations, bending vibration. Out of plane means what? We have this one now. Okay, with respect to this one, out of plane means if both the atoms are come top, both the way comes top, out of plane, otherwise both will be go inside, like this. Means out of plane with respect to this axis, if there two atoms come above or below, above or below, above or below, above or below, it is a what? Out of plane bending vibrations, out of plane same directional rotations means wagging. Out of plane same direction, maybe down or maybe up, with respect to one center atom. If there is a what, this is a out of plane means what? Here is a what? Axis, na? Both are downside now, otherwise both are above. Okay, this is what I am writing. Same direction means out of plane same direction. Out of plane same directional rotation is what? Wagging. Next, twisting. See, this is a plus and minus is twisting. Means what? Same out of plane. If one is above, one is below. If otherwise it is above, it will be below. Okay, means opposite. Out of plane opposite. One is a plus and a minus. Okay, this is a twisting. Out of plane, this is the same direction vibrations. This is same out of plane opposite directions. These are what? Same plane, in plane. In plane, this is a what? And in plane scissoring, the like opposite, and in plane same directions what? Rocking. Okay, and this type of vibrations are possible in IR spectroscopy. And come to this type of vibration, planar and in non-planar molecules. Okay, stretching vibration, then bending vibrations, total vibrations. Then maybe what? Stretching plus bending. This is a what? In planar molecule, the stretching vibrations is n-1, and non-planar molecules, the stretching vibrations are n minus 1. A bending vibrations to n minus 4. Then in non-planar molecules to n minus 5. The total stretching and bending vibrations in a planar molecule is total 3n minus 5, and in non-planar molecules 3n minus 6. Okay, let us see one example. This is a linear or non-linear molecule. This is a planar and non-planar molecules. Okay, the linear molecule example we are taking as a plane. That is a what? Is a linear or non-linear. Okay, let us consider a molecule, linear molecule. This is a what? CO2. The word structure is what? C double bond O and C double bond O. And this is a linear molecule. And here what? C double bond O. These are in one plane. Okay. What is the total number of atoms? Total number of atoms 3. 1, 2, 3. The total number of atoms will be 3. For this total number of atoms is considering as n. Okay. What about the stretching vibrations? Stretching vibrations. For a linear molecule, the stretching vibrations will be n minus 1, n minus 1. Stretching vibrations for a linear molecule. For this linear molecule, the stretching vibrations will be n minus 1. The number of atoms will be what? N is number 3. 3 minus 1 is equal to 2. Total 2 stretching vibrations are possible for the what? CO2 molecule. Okay. And what are the bending vibrations? Bending vibrations. What is the bending vibrations for the linear molecules? The formula is 2n minus 4. So what? 2. Total number of atoms in this molecule is 3 minus 4. 6 minus 4, that is a 2. Total stretching vibrations are 2 and bending vibrations are 2. The total vibrations, stretching plus bending, is equal to what? 3n minus 5. The 3 into n is what? 3, then 5 is equal to what? 9 minus 5, that is equal to what? 4. We get now 2 is bending, 2 is stretching. Total what? 4 vibrations are possible for the linear molecule. This is a linear molecule. That is a one. We are taking the another one. That is a what? A non-linear molecule we are taking. What is a non-linear molecule? H2O, water molecule. Example. Water molecule is a non-linear molecule. What is the structure of this one? This is a one. Okay, non-linear. Okay, the total number of atoms will be, total number of atoms is equal to 3. This is a what? N we are considering. Okay, what are the stretching vibrations? Is equal to n minus 1 for the non-linear only. For the non-linear also, the stretching vibration formula is what? N minus 1. The total number of atoms will be 3 minus 1 is equal to what? Same, 2. Now come to the bending vibrations. Bending vibrations. What is the bending vibrations for the non-linear molecules? For non-linear molecules, bending vibrations will be 2n minus 5. 2n minus 5. 2. What is the total number of atoms? 3 minus 5 is equal to what? 6 minus 1 is equal to, 6 minus 5 is equal to only 1 here. What? Okay. Then total vibrations in a non-linear molecules is, non-linear molecule total vibrations will be what? 3n minus 6. 3n minus 6 is equal to 3 into n is a what? Total number of atoms non-linear molecule is a 3 minus 6. 9 minus 6 is equal to 3. What are those 3? Same. 2 stretching, 1 is bending vibration. Okay, in this way we can calculate the total number of vibrations in the linear and non-linear molecules. Come to vibrational energy level of vibrational energy levels of diatomic molecule. Diatomic molecule. Okay, for this let us consider a diatomic molecule. Consider a diatomic molecule. Diatomic molecule. Okay, for this we are taking HCl, a diatomic molecule. With this we are keeping this chlorine atom here, and here what? This is a hydrogen. Okay, and this we know that the real covalent bond is elastic in nature, means it is in the form of spring model. Okay, is in the spring model. See, of masses m1 m2 masses. Okay, and this is what the real covalent bond is elastic in nature, means that is a spring nature, means it can be compress and elongation. Is there possibility of contrast elongation? Okay, there is a possibility of here, means in this way the vibrations are taking place in this molecule. Okay, like a spring. Okay, and first of all we are keeping here not. Okay, once we are compressing this one, which one? This hydrogen atom. Okay, we are compressing to here. Okay, as we are compressing, at that time some of the restoring force is generated in the molecule. This is a what? Hydrogen. We are compressing here. Okay, as bond length is decreasing, means we are compressing this one. Okay, as the compression of this atom, some of the restoring force is generated in the molecule. As the restoring force is generated, and the same way if we are compressing here now, in this way we are compressing. As we are compressing means at the same force it will come outside. Means what is this? A spring. If you are compressing to this atom, and the same force it will be go elongation. If we remove, we know that what? A spring. If you are compressing, the same way it will be go outside by releasing of that one. Okay, and again we are compressing to smaller wavelength, cell bond length. At this the again it will be comes to this what? As we are compressing it will be go elongation. Once there's a due to the formation, due to the development of this restoring force, it will be go outside with the same force only. As that again we are compressing this one. Okay, this side with the same force it will be go here only. Okay, with this we are writing a form of what? This is the one. In this type of curves are possible. As this is up to distance. Okay, as we are compressing this one, it will be moves towards the longer distance. Okay, what is that? According to Hooke's law, the restoring force, F is what? Restoring force is directly proportional to the distance of the atom transferred as the words. And this restoring force and the distance travel is our opposite direction. As we are compressed inside, due to the formation of this development of this restoring force, the molecule is displaced to more side. It will be displaced more. That's why we are writing what is the minus sign. Minus sign is for the opposite directions. Restoring force and the displacements are in opposite directions. The restoring force as well as this displacement are in opposite directions. That's why we are writing as a what? Minus sign. If you are removing this for proportionality, we have to put a constant or not. This is a what? Kx. And F is equal to what? I am writing positive one minus Kx. Okay, in this way. And see here, we know the frequency. We know the frequency of a spring is calculated by nu is equal to 1 by 2 pi under root k by mu. Okay, this is the distance and this is the restoring force. Okay, and here what? For a diatomic molecule, we have the what? M1 and M2 are two masses, and for this nu of M is equal to 1 by 2 pi under root this k by mu na, where is k is what? Force constant, and mu is what? Reduced mass. Okay, and here what? Mu is equal to what? M1 M2 by M1 plus M2 reduced mass. Okay, and solving this equation, solving the Schrodinger wave equation, we get E energy is equal to V plus of h by 2 pi under root k by mu, where V is equal to vibrational quantum number, then next this is a what? K is a what? And these vibrational quantum numbers may be 0, 1, 2, 3 like this. And this also we know force constant is a reduced mass, and E is equal to V plus of h into 1 by 2 pi. I am writing here what? 1 by this one I am writing 1 by 2 pi under root k by mu. This E is equal to what? V plus of h into, already we know that what? 1 by 2 pi under root k by mu is what? This is the frequency, na? Frequency view m. Okay, and this is the equation for this. Okay, at room temperature, majority of the molecules are in ground state only. Means in a ground state means we are writing V equal to 0. There is a what? Vibrational quantum number is substituting ground state. V is equal to 0 means E0. E0 is equal to what? 0 plus of h into mu. Is a what? E0 is equal to what? Of h Vm for the ground state. Come on to that. If V is equal to 1 for first excited state, if we are substituting V is equal to 1, this is E1 is equal to V is nothing but 1 plus of H nu M. Okay, this is E1 is equal to what? 1 plus of means 1 plus of 3 by 2 H nu M. Okay, with this we are calculating the difference. What is the difference? Delta E nothing but E1 minus E naught. What is the E1? 3 by 2 H nu M minus E naught is what? Of H nu M. By solving this one, what? 3 by 2 minus 1 by 2 of H nu M. That is a what? Giving the what? Here what? 3 minus 1 by 2 na? H nu M nothing but 2 by 2 H nu M nothing but H nu M. Okay, this is a delta E is equal to what? H nu M. Okay, and we know that I am writing the form of wave number. The wave number is what? Frequency by velocity. What is the velocity frequency we got? What is the frequency? 1 by 2 pi under root k by mu. This the wave number is what? 1 by 2 pi of k by mu by c na. Wave number is equal to frequency by velocity of light. This is 1 by 2 pi c under root k by mu. Okay, this is the equation for the wave number. Okay, by using of this one wave number, let us discuss about the factors affecting on IR frequencies. Okay, what are the factors are affecting on IR frequencies? First one is bond length. Okay, and here what? This IR frequency, what in terms of centimeter inverse we write here. Okay, as a bond length. How the bond lengths are affecting on the IR frequencies means, or see the CH, C11H, frequency of C11H. Okay, tell me, by taking of this equation, what is the frequency directly proportional to what? Force constant, and inversely proportional to the reduced mass. Is what is happens here? The CH, what is the hybridization here? What? sp3 hybridization. Alkenes, this is alkene, this is alkene. Alkene sp2. Alkynes, what is sp hybridization? Okay, as here what? As the bond lengths are decreasing or not? Is there more bond length, less bond length, and come back again less bond. As the bond length is decreasing here now, as a bond length is decreasing, bond strength will be increases. Bond strength increases. As the bond strength increases, force constant increases. Okay, what is the order of this one? Bond length decreases. So what has happens? Bond strength increasing. As the bond strength increasing, force constant also increases. As the force constant is increasing, what is the frequency? Is directly proportional to the force constant. Na? As the bond strength is increasing, the force constant also increases. As that frequencies also increases. As the force constant is increasing, frequencies, higher frequencies increases. Okay, means what is the order of this one? Here, comparing to the CH frequency, CH2 frequency is more, and here comparing this C11H frequency, C11H frequency is more. Okay, as the force constant is increasing, bond strength is, as a bond strength is increasing, force constant also increases. As the force constant is increasing, frequency also increases. Okay, this is the one effect. Next, second factor, second one, relative masses of atom. Relative masses of an atoms. What is the relative masses of an atom? Frequency of fluorine, see attached to chlorine, see attached to bromine, and see attached to the iodine. Tell me, what is the masses of the atoms are increasing or not? This is a fluorine. Comparing fluorine, chlorine mass is more, and comparing chlorine, bromine mass is more, and comparing bromine, iodine mass is more. As the relative masses of the atom is increasing, what is happens we see? Okay, as the masses of the atom is increasing, what is mu reduced mass? M1 M2 by M1 plus M2 na relative masses of an atom. This is one as a reduced mass. As the masses of atom is increasing means reduced mass also increases or not? Here masses of an atom increasing. Okay, masses of an atom is increasing. What is happens? Reduced mass also increases. As the reduced mass is increasing, what is the frequency is inversely proportional to the reduced mass or not? From the equation, reduced mass is inversely proportional to the frequencies. That's why as the reduced mass is increasing, what is happens? Higher frequencies decreases. Okay, this which one having more higher frequencies? Fluorine compared to this one. In this way, the higher frequency energies. Okay, then relative masses. Then third one is effect of inductive effect. Okay, plus I effect plus inductive effect. Okay, on the carbonyl functional groups we see CH3 COH. Okay, and frequency of this one comparing frequency of CH3 CO CH3, and before that frequency of H C double bond O H. We see the three compounds. One is about formaldehyde, acetaldehyde, acetone. You see the what happens in the carbonyl frequency. What happened in the carbonyl frequency? Okay, due to here what? No plus I inductive effect groups. No methyl groups na. Here what? 1 plus I effect group. Here 2 plus inductive effect group. 2 methyl groups are donating groups. There is a what? Inductive effective groups are present here. What? As the what happens, is there no I inductive effective groups. Here what? 1 plus I effect. Donating group is there na. What is happens? Here what? Okay. As that the CO strength will be decreases. Okay, here what CO group will be remains. Due to donate inductive group, these strength will be decreasing. Means it will be removed, and here due to the presence of two donating groups, the CO group will be whose CO nature will be losses. Okay, double bond character will be losses. Okay, that's why as the double bond character is decreasing means frequencies also decreases due to plus I effect groups. Means formaldehyde having the more frequency compared to the acetaldehyde, acetaldehyde having the more frequency compared to the acetone. Because of as the plus inductive effect groups are present, the CO character will be decreasing. As the CO character is decreasing, the frequencies of vibrational frequencies will be decreases. Okay, this is end effective. And minus I effect groups are present. Minus fourth one, minus inductive effect groups, withdrawing groups. For example, we are taking CH3CO, CH3. Frequency of this one and comparing the frequency of CH3CO, Cl. Here what? We are removing one of the or substituting one of the methyl group with what? Chlorine. That is what? Minus inductive effect group. We are replacing one methyl to minus I effect groups. What is happens? Due to the presence of this minus I effect group, here what? Due to presence of these donating groups, the CO character will be losses. Here what? Here what? This is the withdrawing group, minus I group. With this, the CO character will be retains. The CO character, because of minus I group, here the CO character will remains. That's why whose frequency of minus I effect group is more than the plus I effect group. Okay. The next fourth one, hydrogen bonding. Hydrogen bonding. Okay, what is hydrogen bonding? A weak electrostatic attractive forces between the hydrogen and the more electronegative atom. Okay, and see, hydrogen bonding generally lowers the bond length. As the bond length is decreasing due to hydrogen bonding, the force constant also decreases. As the force constant is decreasing, frequency also decreases. And we have the two types of hydrogen bondings. One is intermolecular hydrogen bonding, and second one is intramolecular hydrogen bonding. And see here, due to intermolecular hydrogen bond, intermolecular means in between two molecule, or C double bond O of H of one molecule, then another molecule will be R C double bond O H. Here this hydrogen bonding is possible in between these two. This is a hydrogen bonding. There is a in between two molecules. The hydrogen bonding is possible. That is what? Intermolecular hydrogen bonding. Okay. And due to intermolecular hydrogen bonding, the bond length is, this is the CO bond character. Okay. And here what? Intramolecular. This is a intramolecular hydrogen bonding. OH. Here the hydrogen bonding is possible. This is a what? Intra, within the molecule. If hydrogen bonding is possible, there is a what? Intramolecular hydrogen bonding. What is happening first? Due to hydrogen bonding, the CO bond length is increasing. As the CO bond length is increasing, force constant decreases. As the force constant decreases, frequency also decreases. Okay, and here we have the effect of dilution on the hydrogen bonding. We are learning the effect of dilution on hydrogen bonding. As what happens here, in case of intermolecular hydrogen bonding, if we are diluting the solution, and if you are diluting, these two molecules go apart from each other. As the dilution takes place, the two molecules go away from each other. As they go away from each other, there is a increasing in the frequency takes place. Okay, means effect of dilution present here in the case of intermolecular hydrogen bonding. But in case of intramolecular hydrogen bonding, if you are diluting this one, there is no dilution effect. Okay, there is no dilution effect, means as we are diluting, there is no change in frequency, but in case of intermolecular hydrogen bonding, as we are diluting the solution, there is a change in the frequency, because due to dilution, the two molecules go away from each other. With this, the frequency will be changes. But here what, in case of intramolecular hydrogen bonding, as we are diluting the solution, there is no change in the frequency. Okay, this is the effect of hydrogen bonding in carbonyl frequencies. Next, distinguish cis-trans isomerization in IR spectroscopy. Okay, see, generally this is a cis compound we are taking. This is a CH3H. So this is a cis compound, and this is trans compound. Trans means the same atoms are in opposite direction. If the same atoms are atoms or groups are on the same side, this is a cis, and same atoms or groups are on the opposite, that is a what? Trans compound. This is a geometrical isomers. Okay, this cis trans isomer. How you are distinguishing cis trans isomers in IR spectrum? Okay, generally, see here we have the what, this is a donating group, and whose dipole moment direction will be in, this is a donating group na methyl, the dipole direction will be here, and for this one, this is also donating, this the dipole direction will be this, the net dipole direction will be the here, means it have the some dipole moment value, not zero. It have some showing some dipole moment value, not zero, means showing some dipole moment value. But here what, in the case of trans, here what, this is a donating group, that's why the dipole direction will be this side. In case of trans, this is a what, this is also what, the donating, the dipole direction will be what, inside. The net dipole moment value will be cancelled, that is a what, zero. This is a what, opposite na, the net dipole moment become zero, means the net dipole moment is zero, means and here what, the and this is IR inactive, means this shows lower IR frequencies, lower IR frequencies, and trans cis compounds IR active, means higher frequencies. Okay, in this way, means cis compounds observe at a higher frequency, and the trans compound observe at a lower IR frequencies. In this way, we can distinguish cis-trans isomers by IR spectroscopy. Next, types of transition or types of bands in IR spectrum. Types of transitions or bands in IR spectrum. There are 6 types of bands are present in IR spectrum. One is fundamental transitions or fundamental bands. Fundamental transitions are bands. Second one is overtone bands. Third one combinational transitions or combinational bands. And fourth one differential transitions or differential bands. And fifth one is Fermi resonance bands. Then sixth one is hot bands. Okay, let us discuss one by one. For this, we are taking the vibrations to this axis. This is a V0 ground state vibration level, V1 first excited state, V2 is like this, V3. The ground state vibrational energy level is the excited vibrational levels. Okay, first of all, what is mean of fundamental? Okay, in a molecule, vibrations from or transitions from ground state to first excited vibrational level, nothing but V0 to V1 transitions. Okay, V0 to V1 transitions are fundamental transitions, and the bands which are formed by the fundamental transitions are fundamental bands. Okay, V0 to V1, these are what? Fundamental bands. Okay, the next second one is overtone bands. Okay, what is overtone bands? V0 to V2 or V0 to V3, like this. Okay, means by excluding this first one, the transitions from the ground state to second excited state or third excited state, V0 to V2 and V0 to V3 are overtone bands Okay, and due to this type of transitions, the bands will be formed in the IR spectrum. That type of bonds are called overtone bands. Okay, the fundamental bands means V0 to V1, ground state to first excited state vibrations are what? Fundamental vibrations and fundamental transitions, and the bands which are formed by this type of vibrations are fundamental bands. Then V0 to V2 or V0 to V3, what are those? These two are overtone bands, and of this first one, V0 to V2 is first overtone band, and V0 to V3 is a what? Second overtone band. And see, with this, the intensity of first overtone band is more, as the next V0 to V4 means what? Third overtone band, V0 to V4. Okay, V0 to V4 means this is a first overtone band, this is second overtone band, this is third overtone band. As the number is increasing, the intensity of bands will be decreases. This first overtone band have the more intensive than compared to the second intensive band. The second intensive band have the more intensive compared to the third one. Like this, the intensities of higher overtone bands will be decreases. This one having the higher intensity, this one is lower, this is again lower. Okay, this is about the overtone bands. V0 to ground state to first means fundamental vibrations, V0 to higher excited states, V2, V3, V4, like that. They are the what? Overtone bands. In this first overtone, second, third, like that. Okay, the intensities will be decreases with the higher overtone bands. The next third one is a what? Combinational. Combinational means here it is considered two molecules X, Y and Y. Means which type of combinations? Here may be X plus Y combination, or X plus 2Y combination, or 2X plus Y combination. Okay, means the two transitions are combined together to form a combinational transitions. With this, the bands which are formed at that moment are called combinational bands. Okay, for example, we are taking the carbon dioxide molecule. In the carbon dioxide molecule, already we have discussed this is a in this linear molecule. In the linear molecule, how many vibrations are possible here? Total number of vibrations in the CO2 molecule, already we are discussing total 4 in the CO2 molecules. We are discussed this is a total vibrations are possible. Of these total vibrations, we get the total. For example, 4 bands we are getting. Okay, what are the 4 bands in this? For example, 3, then 4, like this. For example, the 4 bands are formed here, and this 4 bands appears at a 665 centimeters. The second one is appearing at 1665 centimeters. Okay, the third one is at 2350 centimeter inwards. Then fourth one is appear at 3015 centimeter inwards. Okay, means of this, what is the combinational means here? What? By combining of this 1, 2, 3 and 4, by adding of these two, combining these two, 1 and 3, 2350 plus 665 gives what? 3015. Means this is a what? Fourth one is a what? One is combinational band or combinational over transition. Means combining these two, first and 3 bands gives the what? The fourth one, combining. Okay, by adding up these two values gives what? 3015. Means this is the fourth one is a what? Combinational band. Okay, the next fourth type of is what? Differential. The differential may be X minus Y, or X minus 2Y, or 2X minus Y, like this may be differentiations. Okay, same combining. Tell me, this is a third and first. We are differential, subtract 2350 minus 665 gives what? 1665. Means the second band. Okay, by adding up these two, 1 and 3, we get the what? Fourth band. That is a what? Combinational band. And differentiating of this 1 and 3, 2350 value minus 665 gives what? 1665. Okay, means the second one is a what? Differential transition band. Differential transition or differential band. This is formed by the subtracting these 1 and 3. Okay, by adding up these two gives the combinational band, and differentiating of these two gives differential band. Okay, this is the fourth type of band. Next, come to the Fermi resonance band. Fermi resonance band. What is Fermi resonance means? See, this is the axis now. V0, V1, V2. Okay, another we are taking V0, V1, V2, V3, like this. V0 to V1 is a what? Already we know that. What is the V0 to V1 means what? First, fundamental band or fundamental transition. V0 to V1 means fundamental transition. And here what? V0 to V2. V0 to V2 nothing but what? V0 to V2 nothing but overtone bands. overtones. Okay, what is Fermi resonance means? Matching of frequencies of fundamental transitions with first overtone band or first overtone or combinational tone. That is Fermi resonance. Matching of fundamental transition frequency with the what? First overtone frequency. That is what? Fermi resonance. Okay, how it is means? Consider the example of CO2, and CO2 molecule is what? This is a linear molecule, and already we know that what is the stretching frequency, stretching type vibrations. Stretching means what? Stretching means symmetrical stretching. Okay, stretching means what? Either here what? Okay. Okay, now outside, as that due to stretching the bond will be stretched same way, otherwise by compression the bond will be decreases. Same na. In this also mu is equal to 0 na. Mu is equal to 0. Symmetrical stretching. In case of symmetrical stretching, mu is 0 means IR inactive. And see here, but it shows a Raman actor. In Raman spectrum, this CO2 shows a stretching frequency of 1347 centimeter inverse in the Raman spectrum. In IR spectrum, it is a inactive molecule because due to symmetrical stretching, the what is that? Dipole moment value is 0. That's why IR inactive na? IR active. But in the Raman spectrum, the stretching frequency is observed at 1347 centimeter inverse for the CO2 molecule. Okay, and this one and same this is about the stretching. Come to the bending vibrations of CO2 molecules is observed at 667 centimeter inverse. 667 centimeter. That bending vibrations of CO2, the symmetrical stretching value will be IR inactive, but in the Raman spectrum it shows a fundamental band. This is a fundamental transition band observed at 1347, and this is what bending vibrations of CO2 is 667. Okay, and what is that? This is the what? Fundamental of bending vibrations. And what is the overtone means what? Already we know that. What is the overtone? V0 to V2, nothing but first overtone. First overtone means what? First comparing this one, this is a 2 into x value. For example, x is the what? Fundamental vibration value means what is the 2x is the what? First overtone vibration value. Okay, for example, we are multiplying this 667 into 2. 667 into 2, that is gives what? Approximately 1347 centimeter inverse. Is matching or not? What is the Fermi resonance? Matching of frequencies of fundamental vibrations. Fundamental vibration value is what? 1347. This is matching or not with the which one? This is the fundamental bending vibrations of CO2. By multiplying with the 2 means gives the 1347. Means these two are equal when this is the what? This is the first overtone vibration or combination. Or combination means what? We are some doing what with the multiplying with the 2. We are doing some combination. Okay, means matching of this fundamental vibrational frequency with a combination or first overtone vibration is what? Fermi resonance. Is a Fermi resonance bands. Okay, understood now? The next last one is hot bands. Hot bands. Okay, what is hot band means? See, this is a V0, V1, V2 like this. In the ground state, we have the, for example, 5 molecules is there now. Is a 5 out of these 5 molecules, hot bands means we are increasing the temperature. If we are increasing the temperature, what is happens? The population in the ground state will be decreases. Means some of the molecules are transferred to the ground state to the first excited state. Due to the increasing the temperature, some of the molecules are excited from ground state to the excited state, are transferred from transitions are possible here from ground state to the first excited state at the temperature. Here what? Next V2 na, V3 like this, V4. Okay. Okay. Initially, by increasing the temperature, the population at a ground state will be decreases, and some of the transitions that takes place, and some of the molecules are transferred to the excited state, and from here now the transitions are possible, V1 to V2 or V1 to V3 like this, V1 to V4. Okay, this type of transitions, higher transitions. What is that? Higher transitions. Not this is a zero, not zero na. Already. What is that? V0 to V1 nothing but fundamental. V0 to V1 fundamental. V0 to ground state to excited higher states. V2 V3 nothing but overtones. Combinations means what? Combining. Differentiate. Fermi resonance means what? Matching of ground state, fundamental vibrations of fundamental frequency with the what? First overtones is the Fermi. Hot band means what? Transitions takes place at a higher energy levels. That is what? Higher transition levels. Here V1 to V2 or V2 to V3 or V1 to V4. Higher transitions are what? Hot. The transitions takes place in the higher vibration levels. At the time the bands will be formed. The type of bands are called hot bands. Nothing but V1 to V2 or V1 to V3 like this. V1 to V2. Higher transitions are what? Due to higher transitions, some of the bands will be formed in the IR spectrum. The type of bands are called hot bands. Okay, these are the types of transition or types of bands in the IR spectrum.